Hey, everybody. Happy Friday to you. Um, I was out walking with my wife around the pond, and I was just talking about how different classes were going. And I suddenly realized that for the first time in almost 2 months, I'm actually teaching you guys something today. Um, it's been a while. I guess when we finished up series, that was the last time. And I think, if I remember right, that was just a few days after we were done with each other in the classroom. But here we go. I get to teach you guys something new before the end of the week, before we're done with our time together this year. Um, the next chapter, I've mentioned this already, it's just going to be about exposure. As I've prepared this lesson, most of what I've been doing is taking 2 or 3 lessons and picking and choosing. These are the important skills. These are the things that will hopefully help you out the most as you move forward. For those of you who do move forward in mathematics or calculus, or in maybe other sciences where you would see stuff like this, which probably makes you wonder why I have a picture of an Etch-a-Sketch on the screen right now. My son was wondering the same thing. My seventh grader, uh, walked by probably expecting to see some high-level mathematics and instead saw an Etch-a-Sketch. But I think this is the best illustration of what we are doing when we have parametric equations. A parametric equation, or a parametric set of equations, which we'll see in just a moment, it takes, well, maybe I'll put the definition up here first. Our location, the x and y coordinates of our location, are both functions of some other parameter, hence the name parametric equations. So x is a function of t, which I usually think of it as standing for time. As time is changing, the x coordinate is doing this, and the y coordinate is doing that. And so x is doing one thing, y is doing another. And it's not y as a function of x or x as a function of y. It's both of them independently as a function of time. So what I think about with the Etch-a-Sketch is, as I turn the knob on the left, and I'm not even sure about this, but if I turn the knob on the left back and forth, we end up with motion that is just moving horizontally. And then if I start moving the knob on the right, I'm moving vertically up and down. And if I move them both at the same time, well, then I can get different motion and different shapes and all kinds of cool stuff that you can draw on an Etch-a-Sketch. This is not y as a function of x. This is like no f of x we've ever seen before. But if we look at what the x is doing, if we look at what the y is doing, acting independently, we can end up with some pretty cool diagrams. Um, there's some pretty incredible Etch-a-Sketch art out there if you look for it. We'll be doing stuff that looks a lot more simple than that. And actually, we're not going to do a whole lot of graphing. I just want to make sure that we're okay with this idea of x and y acting independently. So if I want to graph this set of parametric equations, x is equal to t squared and y is equal to 2t. This being the first time we're doing this, I'm going to think of it very procedurally, where I'm going to make a table of values like you've done in the past when you graph y as a function of x, when you first graphed a sine function, when you first graphed an exponential function, when you first graphed a line. You probably just made a quick t-table, put in some values of x, and then figured out what the value of y was. Well, we're going to do the same thing here, except I'm going to put in values of t. Now, given the size of the graph that I've got here, given the functions that we're doing, I know that the good values of t to use are going to be between -3 and +3. And so from -3, -2, -1, 0, 1, 2, 3, these are my inputs. These are my independent variable values. And then x and y both depend on what t is. So I use the x function to figure out what the value of x is. X is equal to t squared. So -3 squared is 9. -2 squared is 4, -1 squared, etc. And then my y values, the y values are 2 times t. So 2 times -3 is -6. 2 times -2 is -4, etc. And so we end up with a table of values that looks like this. And now when I graph this, this is still the x-axis. This is still the y-axis. There is no t-axis. My points on the coordinate axis system are just functions of time. And so at time equals -3, my location on the graph is 9, -6. The point 9, -6 over 9 down 6. That point right there is the location at time equals -3. At time equals -2, we've got 4, -4 right there. At time -1, I've got 1, -2, and then 0, 0, 1, 2, 4, 4, and 9, 6. And so I get a graph that looks like this. It starts at this point at time equals -3, and then it moves in this direction, and then changes and moves around in this direction. Y is not a function of x. We are violating the vertical line test, and I went a little bit too far there. If I only want a graph between time equals -3 and 3, it would look like this. And actually, on a lot of these graphs, you'll see arrows indicating that this is the direction that it's going. If I change my function around, if I make this y equals -2t instead of +2t, this would have been the same curve, but it would have been going in the different direction. And if I don't restrict my domain, if I say let's go for all values of t, then this is a parabola that goes infinitely down into quadrant 4 and infinitely up into quadrant 1. But at least this part of it, just between t equals -3 and 3, we get a graph that looks like that. Imagining on our Etch-a-Sketch, the x value is decreasing pretty quickly and then increasing, and the y value is just steadily increasing. So the knob on the right side, we're turning at a constant rate, increasing the y value, and then the x value is decreasing fairly quickly and then slowing down and then increasing to give us a graph that looks like that. So what if I have a curve, a parametric curve that looks like this? X is equal to cosine and y is equal to sine. So as I think about this, I'm going to think about this in terms of the components. What is the x value doing? What does cosine do as time goes by? What is y doing? What is the y value? What is sine doing as time goes by? So the window that I have set up here, I know that both sine and cosine are between -1 and 1, so I know I'll be somewhere on this. And so my functions and trig students are very familiar with sine and cosine curves right now. I think in this case, let's just graph between 0 and 2 pi. Both of these are periodic functions with a period of 2 pi. So if I know what it does between 0 and 2 pi, I'll know what it does everywhere. And so as I'm thinking about the x values, I'll start with this. The x value is cosine. Now again, my functions and trig students know that between 0 and 2 pi, we know what the cosine graph looks like. At time equals 0, it starts off at 1. So my x value starts off over here at x equals 1. And then as time goes by between 0 and 2 pi, I know that the x value is going to decrease down to -1 and then increase back up to +1. So on my Etch-a-Sketch, I'm starting over here on this side of the screen. I'm going to go to the left and then back to the right. But at the same time that that's happening, my y value is doing what the sine curve does. The sine curve starts at 0, so vertically I'm at 0, and I know that the sine curve is going to go up to 1, and then down to -1, and back up to 0. So the question is, what does this curve look like when both of these things are happening at the same time? Starting at an x value of 1, decreasing, and then increasing, while the y value starts at 0, increases, then decreases, then increases. Well, let's play a little connect the dots. Let's put some points on here. At time equals 0, my x value is 1, my y value is 0. At time equals pi over 2, after pi over 2 for the time, now my cosine value is 0, but my sine value is 1. After another pi over 2, so at time equals pi, I'm over here. My horizontal, my x component is -1, and my y component is back at 0. At time equals 3 pi over 2, cosine of 3 pi over 2 is 0, and sine of 3 pi over 2 is -1. And then by the time I get to 2 pi, I'm back to where I started. Now, what it looks like in between, maybe it looks something like that, or maybe it looks something like that, or maybe it looks something like that. Tough to tell without thinking more about this. And so maybe I do a little bit more fine tuning between 0 and pi over 2. How about um, how about pi over 4, halfway in between? So thinking about 45 degrees. Now cosine and sine are both going to be square root of 2 over 2, which is about zero point 0.7. So if I'm to the right by zero point 0.7 and up by zero point 0.7, we're going to be somewhere up right about here, I think. So looks like we're going to have a curve that's doing something like this. And at this point, I'm going to say, if you are shouting at your computer screen right now saying, but Mr. Crowett, don't we know what this looks like? Well, then I'd say, yes, stop shouting at your computer screen. Let's be civilized about this. But when you defined the unit circle back in, man, Algebra 2, functions and trig, maybe pre-calculus, this is how we defined the x-coordinate on the unit circle. X is cosine, y is sine. What we have here is actually a graph of the unit circle. And I'm going to add arrows to show that we're moving in this counterclockwise direction. And there we go. There's a parametric curve. Now, when we do calculus with parametric curves, even if I've got a crazy curve that looks something like this, and we'll come back and look at this when we talk about vectors, how fast the curve is moving might be something that is a factor. But at least for right now, when I talk about calculus, if I'm talking about the slope of a tangent line, well, slope of a tangent line, I'll just give myself a tangent over here. Slope of a tangent line at this point, well, that depends on how fast y is changing and how fast x is changing. And it turns out to work out pretty well. If I look at how fast x is changing, this looks like related rates. dx dt, how fast is x changing with respect to time? dy dt, how fast is y changing with respect to time? And if I think about this in terms of slope, slope of a tangent line is change in y over change in x. And that's what we're looking at here. This is how x is changing, dx dt. This is how y is changing, dy dt, which makes my formula make a whole lot of sense. The slope of a tangent line is still dy dx. But because y and x are both changing independently of each other with respect to time, how fast y is changing is dy dt, how fast x is changing is dx dt. So dy dx, the slope of a tangent line, is dy dt over dx dt. And the little caveat over here says that, well, we have to be careful. If dx dt is equal to 0, if there's no horizontal motion, then we may have a vertical tangent line which doesn't have a slope, but that's old news. As long as dx dt is not 0, this will give us the slope of a tangent line. And this is interesting because if I have a curve that's doing something like this, I'm looking at this little section of the curve right here. It's moving from left to right, dx dt is positive, but it's also moving from low values to high values vertically. So dx dt is positive, dy dt is positive. So at this spot of the curve, dy dx, the slope of a tangent line, would be positive. But then we also have a section, let's see, how about, I'm looking for a good spot to demonstrate this. I'm going to go with this little section over here. So here's a spot where the slope of a tangent line was positive, but I am going to go over here also. Let's take a look at a section that's over here. No, that's a bad choice. Oh, I guess I'll go with the section that I've got over here that I already have a tangent line drawn in. As the curve is moving, the x-coordinate is decreasing. It's moving from right to left. The y-coordinate is decreasing. It's decreasing over time. It's moving from high to low. And so the slope of the tangent line is positive, even though it's moving to the left and moving down. dy dt and dx dt are both negative, but we still have a positive slope. And of course, a negative divided by a negative would give us a positive. So that also does make sense. Okay, I'm yapping too much. I'm spending too much time talking about some of the specifics of this. Let's actually take a look at a specific problem. Suppose I have a parametrically defined curve according to these parametric equations. If I ask for what values of t does the curve have a horizontal tangent line, we can't just say the derivative is 0. That was when we had y as a function of x. When I say a horizontal tangent line, that means that there's no vertical motion. All of the motion is horizontal. So dx dt could be anything except for 0. If I have a horizontal tangent line, if there's no vertical motion, that means that dy dt would be equal to 0. And so if I write that down, dy dt, I'll call it y prime. Dy dt is going to be 2t plus 3t squared. And if I want to find where that is equal to 0, it might be helpful to have it in factored form. Let's pull a 2t out of there, and I'll be left with 1 plus 3t. And so if t is equal to 0, there will be a horizontal tangent line. Or when t is equal to, I guess it would be negative 1/3. Those will be the spots where we have a horizontal tangent line. Actually, I better be careful. I guess at time equals 0, dx dt would be equal to 0 also. So actually, at time equals 0, since both dy dt and dx dt are equal to 0, I guess the particle is stopped at that moment, or the motion, the curve is not moving for that moment in time. So we'll have to look at a little bit more closely to see if that's horizontal or vertical. But definitely at time equals negative 1/3, because dx dt is something negative. Dy dt we see here would be equal to 0, so it would be a horizontal tangent line. Describe the behavior of the curve at time equals 0. So dx dt, I guess I'll write that here. X prime is 2 times t. So at time equals 0, 2t, 2 times 0 is equal to 0. So there is no horizontal motion. At time t equals 0, 2t is equal to 0. So there's no vertical motion. So if I describe the behavior of the curve at that time, I'm just going to say that it's stopped. There is no motion. It's not moving left or right or up and down. My fingers are off of the Etch-a-Sketch knobs. And then finally, for what values of t is the y value decreasing? Well, that's going to happen when dy dt is negative. So if I look at what my dy dt looks like, let's see, y prime was, did I make a mistake? Oh, sorry. When I factored a 2 out of this, I'm sure someone, again, was yelling at their computer screen, which kind of odd behavior, but who am I to criticize? Let's see, this would be over 3/2. So instead of negative 1/3, it should have been at negative 2/3. But let's get that back over here. 1 plus 3/2 t. And so if this is my y prime, when is the y value decreasing? That's going to be when y prime, when dy dt is negative. And so I'd have to take a look at, I would maybe make a number line for something like this. I know that at time equals negative, what do we say, negative 2/3. It's equal to 0. At time t equals 0, it's equal to 0. And so then I'd plug in values less than negative 2/3, where, let's see, this quantity would be negative and this quantity would also be negative. So negative divided by negative, or times negative, is positive. At times between negative 2/3 and 0, we've got a negative times a positive. And then finally, when t is bigger than 0, dy dt is positive. So when is the value of y decreasing? It's going to be between negative 2/3 and 0. Specific question that we're looking at right now, but that's what we're thinking about. What is happening to the y value? We're looking at dy dt. What's happening to the x value? We're looking at dx dt. And then finally, wrapping things up, let's take a look at arc length. We've done this already in function mode. And when we did this, I probably spent some time in class deriving this formula and showing you where it came from. And I used some form of a distance formula. where delta y and delta x, if I've got a little small chunk and I want to look at the length of this section, we do Pythagorean theorem. Delta x squared plus delta y squared equals that distance squared. So that distance is the square root of delta x squared plus delta y squared. And I did some factoring and I pulled some things out and did some simplifying to give the equation for the integral of arc length. And if you remember it, great. If you don't remember it, it looked something like this. The integral from one value to another, this is in terms of time. So we're integrating from one time to another, from some time to some other time. I used alpha and beta here for no reason other than I didn't want to say T1 and T2. I just wanted to give it some values. And then this dy dt looks familiar. It was dy dx in the formula, but everything's in terms of time now. So instead of dy dx, it's dy dt. Instead of 1, which was really a factored form of dx dx, we're looking at dx dt. Now, as far as what you're doing this year, as far as what we're doing in this class right now, this is just a formula that I want you to be familiar with using. This is just change in x, change in y, and the rest of this is just coming from Pythagorean theorem and integrating to take a whole bunch of infinitesimal little sections and putting them together. In terms of what we're doing, it actually works out pretty well. This is going to be stuff that you'll be able to do in your calculator. And so let's finish up with this quick example. I don't know how quick it'll be, we'll see. Take this parametrically defined motion, the same stuff that we were just looking at before, and I want to talk about the difference between displacement and distance traveled over a span of time, between time equals -2 and time equals 3. I'm going to start with what you maybe did in pre-calculus. Honestly, I don't know how much of this stuff you did in pre-calculus, but in pre-calculus, if you looked at parametric curves at all, you could find displacement. Displacement is just the distance from where you started to where you finished. And so find where it is. At time t equals -2, plug it in. This is the location, the x-coordinate and the y-coordinate at this time. Plug in time equals 3. Here are the x-coordinate and the y-coordinate just plugged into my parametrically defined functions. And so there it is. From this point to this point, and now this is a problem my geometry students do. What is the distance between these 2 points? And this is distance formula. The x value changes by 5, the y value changes by 40, 5 squared plus 40 squared, and take the square root. If you want to use the distance formula, x2 minus x1 squared plus y2 minus y1 squared, take the square root, we get about 40.311 as the displacement. That's the straight line distance between the location at the beginning and the location at the end. And so what we just learned with our new formula is that the distance traveled is this integral. I'm integrating from time equals -2 to time equals 3. Those are giving my limits of integration. I've got dx dt is 2t, and I've got dy dt is 2t plus 3t squared. Plug them into the formula. And I did not even attempt to do this one by hand. I plugged this into my calculator using the fnint function of my calculator. And when I did that, I got a little bit bigger than what the displacement was, which, by the way, makes sense. Your distance traveled will always be greater than or equal to your displacement. The parametric curve we're looking at here is a curve. It's not a straight line. And so we see that the distance traveled is a little bit more than what the displacement was. For your assignment, I've got you doing a couple problems like these, and I do want to stress that you should not feel like you need to do them by hand to get an exact answer. In fact, I don't even think I assigned any of those problems. Use your calculator, get an approximation. The actual assignment looks like this. Your first assignment of new stuff in quite some time. Just a few questions, 5 questions from section 10.2, and this is from the same book that you've been using all year, but it's been a while since we've done this. So I will post a PDF with the problems along with the assignment. And so just like always, put your answers on a separate sheet of paper. This assignment should not take you nearly as long as most of the rest of the assignments for this class. Just a little bit of practice finding slopes, a little bit of practice finding distances, and that is all we are looking for today. So there we go. That was a little bit longer than I expected it would be. but hopefully the assignment doesn't take you all that long. Um, have fun with this. Good luck, and golly, I guess a week from right now it'll be our last day together. So um, there we are. Great. Have a great weekend, and we'll see you on Monday. Bye bye.